I got one more lecture I got to give, and then it'll dovetail into the next lab. Okay. So last time I talked about control theory and the notion of bounded input, bounded output stability. And the idea is when you have a transfer function or an agglomeration of transfer functions that are convolved together, ideally, if you have a bounded input, finite input, you should get finite output. But I mentioned that in practice, even a physical system or a control system is not going to explode to infinity. I mean, everything has its limits. But the idea with stability criterion is that you want the system to stabilize or to converge on a set point of your choosing, right? That's the idea of stability. So we talked about how a few different ways to determine if a system was stable or not. And then at the end of the lecture, I talked about discrete transfer functions. So most of the time I spent talking about S-domain transfer functions, and that's continuous. But when you design a controller on a CPU, it's a discrete system. So you have these sample points where you evaluate the system state and make control decisions. And one way to conceptualize that is through the Z domain. And we talked about how to convert from S domain to Z domain through the Tustin transform, right? Everyone clear on that? Okay, so my point is that when we did that with the Tustin transform, there was a part of the Tustin transform is, you basically plug this in for S and you get a Z domain, right? But there's a little detail in here. There's this time step in here, the T sub S. And that is your time step or the sample period, right? So the problem is that if you design a stable control system in the S domain, but then you convert it into the Z domain, that does not guarantee that it will still be stable. And part of that stability is going to depend on that time step value that you use. That makes sense? So you could have a stable transfer function in the S domain, you convert it to the Z domain, but your time step is too long, and suddenly now it's unstable, right? So that time step is important for control systems. And generally it needs to be tuned, right? To ensure that you don't want it to be too small, but if it's too large, then you can have an ineffective control system. Which leads me into this next lecture on real-time systems. So as you guys know, most operating systems and architectures are designed to minimize the average case execution time. Right? So, when you go buy a GPU, new GPU, you're trying to bring down the average case execution time, right? The problem is that if you have a control system and you design it for a specific time step, you have to ensure that you have a bounded worst case execution time, right? That meets that time step, right? So most real-time systems are control systems, and they have some time steps involved, which gives you a worst case, a deadline, what they call a deadline, an execution deadline. So in a real-time system, you may have actually a higher average case execution time than a normal computer or normal operating system. But the goal of a real-time system is to bound the worst case execution time. All right? So Linux, which is, I guess, probably the most popular operating system in the world, right? Has no facilities whatsoever for saying deadline. This task must complete by a certain deadline. It tries its best, but it makes no guarantees. So if you design a control system on Linux, you're in trouble. It's not going to work. So for that reason, there are specialized operating systems that are designed for real-time systems that do what Linux cannot do, which is guarantee a given worst-case execution time. So, for example, it's kind of unclear how you measure worst-case execution time. So the problem is that on a CPU you have non-deterministic behaviors in there. You have cache misses, and if you have a virtual memory system, you can have page faults, you can have interrupts. We talked about interrupts in class. It's really hard to tell or determine what the worst-case execution time is, and that's even assuming that you just have one task running, right? And the task, its behavior is agnostic to the data. In other words, it doesn't have any control-dependent, features in it, if statements, right, where there's different control paths, right? So one way that you can estimate the worst-case execution time is you can run a task a whole bunch of times and you can collect statistics. And some tasks may exhibit a certain, distribution of execution times when you run it over and over again, right? And so if you have, for example, a normally distributed set of execution times, you can estimate the worst-case execution time by measuring the standard deviation and the mean. And then if you go, for example, 3.719 standard deviations above the mean, that would give you the worst case execution time, but only with a 99.99% confidence. Okay. Likewise, if it's 3.09 standard deviations, it'll be 99.9, and 2.326 standard deviations is 99% confidence. Now, this is assuming, of course, that it's a normally normal distribution, right? Make sense? Okay. So, for example, assume you measure a task execution time for 10 runs, and then you get the following data, 12 milliseconds, 13 milliseconds, 14. And again, these different numbers are coming from a variety of things in the system that cause the run time to vary from run to run. And by the way, this is going to happen the variance of these execution times tends to be much wider on like an operating system like Linux. If you do it on bare metal, where you don't have an operating system, this variance closes up a little bit, right? But it's still not zero. You still get some variability. There's really only one way to get like a zero variability of execution time, and that's an FPGA, basically. You have to put your design on FPGA, and the FPGA can't have things in it like DRAM controllers and on-chip networks, network on chips, all those kind of things can still introduce this uncertainty. But anyway, getting back to this example, if you measure it for 10 runs and then I ask you what the worst case execution time is with a 99.9% confidence interval, all you have to do is calculate the mean, which is 20.5, the standard deviation, which is 9.2, and then you have to add 3.09 standard deviations to the mean, and you get 48.9, right? So you can estimate that. Now, the other thing, though, is you might notice that some of these measurements seem to belong to one class. Like you've got 12, 13, 10, 14, 11, and then you've got this other group that's 30, 27, 25, 31, 32. So if you look at the data, you see that, well, maybe this thing is running in like two modes, right? Like depending on what data it gets. It may take one branch or another, right? And so if you know that, if you know how the software works, and you know that for sure, then you can group this into two modes, right? Where you group the first 5 measurements have a mean of 12, the second 5 measurements have a mean of 29, the first 5 measurements have a standard deviation of 1.6, and the second have a standard deviation of 2.9. And so the advantage here is that the individual standard deviations of these two groups is much less than the standard deviation of all the data collectively. And so as a result, you can get a tighter worst case execution bound by looking at the mean of the second group, which is 29, and adding the 3.09 standard deviations to that one. So that's 29 plus 3.09 times 2.9, and that one is 38, right? Right. Now, of course, you would do that to both groups, but that second group is the one that's going to give you the higher number there, right? Make sense? Yes?
The 3.09 isn't like a magic number, it just directly maps to 99.9%.
Yeah, it's the confidence. It's what you get in the back of the statistics book. Okay, so now the issue, though, is that's just talking about one task. The real challenge comes is when you have multiple tasks competing for the CPU, right? Which is pretty typical in a control system. You might have one microcontroller, and then you have, like a robot where you're independently controlling the different, limbs or arms or wheels, right? Generally don't have just one dedicated microcontroller for everything you're controlling in a system. So that introduces this problem of scheduling. So for example, if you have 4 tasks, and each task would be basically a control loop, right? A controller. And each one may have a different, what I show there is computation time, but that's actually the worst case execution time. And then a deadline. Deadline could be, for instance, when you have to finish, obviously, but the time step, essentially. Now, in this case, I'm not assuming it's a periodic task. This is a simplified case where I start these guys all at the same time. They only run once, and each one has just one deadline, okay? So, but even in that case, there's 24 possible ways that you can schedule this, assuming there's one CPU, right? So if you can only put one task on the CPU at a time and you run each one to completion, then there's 4 factorial possible ways to order those. And so I thought it would be fun to actually fully enumerate all of those, look at every possible ordering. So for example, in this first case, you run task 4. I reused my waveform code for this, my timing diagram code. So you run task 4 first, and then task 3 second, task 2 third, and task 1 fourth. Now, no matter which order you use, you're going to finish these guys at the same time, which would be obviously the sum of the execution times. The completion time for all 4 tasks is always the same. The difference is when you complete each individual task. And so in this case, in this first ordering, in this first schedule order, I put little lines on here to indicate where the deadlines are. These little, I don't know if you might not be able to see these really well in the back, but there's these little red vertical lines here. That's your deadline for each task. And so task 3 meets its deadline, just barely. Task 4 meets the deadline pretty easily, right? Task 2 meets its deadline because it finishes way before its deadline, right? But task 1 misses it, it busts the deadline, right? It's still running when its deadline happens, right? But if you sort them in this other order, right, where you run task 4 and then task 3 and then task 1 and then task 2. So in this case, the only change I made is I swapped 1 and 2, I think. Yeah. All you do is swap task 1 and 2. Then all 4 meet their deadlines suddenly, right? And then, so order 2 meets the deadline. Then there's order 3 is task 4, then task 2, then task 3, then task 1. That one blows the deadline on task 1 and 3. And then I've got 4, 5, and 6, those different orders, they all miss a deadline. 7, 8, and 9 are 3 more orders, and number 8 does actually meet all the deadlines, but 7 and 9 do not. And then 10, 11, 12 miss, 13, 14, 15 miss, 16, 17, 18 miss, 19, 20, 21 miss, 22, 23, 24 miss, right? So out of the 24 ways to schedule this, only 2 meet the deadlines. And so if you look at the 2 that met, you can kind of get an idea of what strategy was employed there. I mean, because obviously it's not practical to do this full enumeration. So the number 8, number 8 effectively assigned priority to these tasks. Priority being the order in which they're scheduled, based on their deadline. So the earliest deadline here was task 3, so he was scheduled first. Then task 4 was the second earliest deadline, and then task 1, and then task 2. Right? So just using the kind of the simple policy of whoever has the earliest deadline, you should do that one first. That worked. And then this one, number 2, also worked, which was a different ordering, but it turns out this one was using least slack first. So slack is just the difference between the deadline and the execution time, right? And so whichever one has the least amount of slack, you can schedule first, and that one worked for that one. However, this one is shortest task first. The shortest task is 2, then the next shortest is 3, then 4, then 1. That one didn't work. So scheduling based on the execution time doesn't work, but scheduling based on the deadline and the slack seemed to work in this case. So the problem, though, is that this is actually, when you have a real-time environment, usually you don't just run these once. Usually the deadline is the deadline, but it's also the period that you're running the task at. So when the deadline elapses, then that task becomes ready to run again. And then its next deadline will be, the whatever the period is, added to the end of the current period, right? You guys with me? Right? And this would be just a classic control system where you have a time step. So the time step would be both the rate at which you run the task and the deadline. You have to complete the task before the next time it's run, obviously. Or you risk the control system becoming unstable and driving your car off the road, right? So that's called periodic scheduling. And so this is a much harder problem than what I just showed. In this case, you have a worst case execution time, and instead of a deadline, I call it period, which is the same as the deadline, but it's also the rate, or the inverse of the rate at which you run the task. Now, the first thing that you'd want to look at, like say you have a set of tasks and you have a set of corresponding times and periods, the first thing you want to look at is the utilization of the CPU, because if you add up the ratios of each one of these computation time divided by the period, that's going to give you the utilization of the CPU, right? And obviously that can't be greater than 1, because then it's not physically possible to schedule those guys, right? That's a really easy indicator that there's a problem. So in this case, you look at this, and if I look at this, I'm saying, well, 40 out of 76, 6 out of 84, 14 out of 35, 20 out of 37 looks reasonable to me. I don't see a problem with that. I mean, look, these are pretty sparse. But if you add up, if you calculate the utilization, which is the sum of the times over the periods, it turns out that this is way overcommitted. The utilization is 1.53. So there's no way you could schedule these. It's impossible, right? So, but obviously, if the utilization is less than 1, then it may be possible. But then the question is it? So there's 2 very classical approaches to this. The first is earliest deadline first scheduling and rate monotonic scheduling. So earliest deadline first is where you schedule a task, whatever task has the earliest deadline coming up, right? Now you might say, well, that's common sense. What's so revelatory about that? Well, you have to keep in mind that the problem here is that after you get done running a task within its current period, it's not ready to be run again, right? So its deadline doesn't exist until the next period of that task comes. And then suddenly its deadline exists, right? You guys with me? So when you're evaluating EDF scheduling, what you're doing is you're calculating the priority of each task, but you have to continuously recalculate the priorities as you go. Now, technically, you only have to do it whenever a task finishes or whenever a task's period begins, right? But that's often, right? That happens a lot. So the problem is that it's just not practical, because what ends up happening is that as you march through time, the priorities of the tasks are continuously changing, meaning they have dynamic priority, right? And I've never seen an operating system that can do that. That's completely infeasible, right? However, the good news about EDF is if you could do it, you could schedule any set of periodic tasks as long as utilization is less than or equal to 100%. And assuming that it is a preemptive scheduler, meaning that when a task with a higher priority suddenly starts its period, it's allowed to cut in and run and interrupt a currently executing task, right? So assuming you have a preemptive scheduler and you can apply dynamic priorities, continuously adjust the priorities, then no problemo. As long as the utilization doesn't exceed 100%, you're good to go. But like I said, nothing can do that. It's just too expensive, not practical. The more common approach is called rate monotonic scheduling. And in this case, you assign priority to tasks. And by the way, let me just to clarify that too. The reason why you have dynamic priority with EDF is because the deadlines are relative to the current time, right? That's what I'm trying to say, right? The deadline for each task, in terms of how early it is, depends on where you currently are in time, right? Now, with rate monotonic scheduling, the difference is that every task has a fixed priority based just not on its deadline, its next deadline coming up relative to current time, but instead its priority is just based on its period. The lower the period, the higher the priority, right? Does that make sense? So when a task becomes ready, if its period is lower than the task that's currently running, then you swap it in. You context switch and you put it on the CPU, right? Very simple, right? But there's a big downside. The downside of rate monotonic scheduling is that it's not optimal. You can fail to schedule a set of tasks even if the utilization is less than 100%. So your utilization of your task set may be fairly, well, I don't want to say fairly low. It can be less than 100%, and you're thinking, no, it should work, right? And it doesn't, because it's just not capable of scheduling, right? So here's an example of, this is earliest deadline first. This was tricky. Okay, so the problem is you got 3 tasks, and they all have different periods, right? But they're not harmonics of one another, right? They're 40, 50, and 20 as the periods, right? So then and then the run times are 10, 15, and 5. So I created this. This was such a pain to set this up. So I generated this schedule with EDF. And the periods are marked now with this thicker red line that's easier to see. And you can only run, it's one CPU in this case, only one can run at a time. And this shows, basically, what's going on. This is the schedule for EDF, right? But in order to figure this out, like I said, you have to, every time a task ends or a new task becomes ready, you have to recalculate priorities. Make sense? Okay. And in this case, the utilization is 80%, which means that there are 20% of the times here where nothing is running. Like, for example, right here, you can see 0, 0, 0. At this moment in time, nothing's running, right? Okay, so with rate monotonic scheduling, I rewrote this And like I said, you basically give every task a priority that matches its period. And I think this one was good, right? Did we miss any? I don't think we missed any. I don't see task one. I don't know. We're good here. The problem is that it's a little bit difficult to tell when a task ends because you'll notice this task 2 starts here and then it goes dead, right? But why? Because it got preempted, right? But then it comes back here, it picks up where it left off, and then it goes dead here again. Why? Because it finished, right? So task 2 dropped, task 2 stopped here because of preemption and it stopped here because it finished, right? And that the timing diagram doesn't indicate the difference. Actually, I could have done that, maybe color-coded it or something. But yeah, so that's what's happening there. That one looks good. Okay, here's another example though. So this one has 3 tasks, 4, 10, 4 out of 10, 3 out of 12, 5 out of 15. Utilization here is 98.3%. I ran this with RMS and I ran this with EDF. No problem with EDF, but RMS busted the deadline here. Okay. Now, what's crazy about this is look how long it took it before a deadline was violated. So even if I were to test this through simulation, this is the real challenge, is that if you wanted to know if RMS works for a given task set, you might say just simulate it. I mean, you did it. You simulated it. You ran it, right? But there's no way to know how long to simulate it for. You never know when this might happen. It could take a long time before a task misses its deadline, right? So this is not a viable option for determining if you can schedule these real-time tasks. So for that, there's these schedulability tests. So RMS actually has gone through several, at least 2 that I know of, schedulability tests. The first one was created it was in a very famous paper by Liu and Leyland, I think in the 80s. And now, so that one basically said that you can guarantee that you can schedule with RMS as long as the utilization is less than some number. I think it was 69%, right? It was just a constant magic number, right? Now, if your utilization is more than that, they don't say it can't be scheduled. They just say, maybe, maybe not. No one knows, right? So these schedulability tests tell you there's 2 outcomes here. One outcome is definitely yes, can be scheduled, or unknown. Maybe it can, maybe it can't. If you want to try it, then no guarantees, right? As far as I know, all these schedulability tests work like that. So the newest one that I can find for RMS, this one is you take each of the run times divided by the periods, right? And you add them to 1. And then you multiply them all together. And if that product is less than or equal to 2, then that guarantees that you can schedule. If it's greater than 2, then it's like, no comment. It's unclear. It doesn't mean it can't be scheduled, but there's no guarantee that it can. Okay, so for example, if we have this task set, 10 out of 40, 15 out of 50, 5 out of 20, you just do you just multiply these guys up. So 1 plus 10 over 40 times 1 plus 50 over 15 over 50 times 1 plus 5 over 20. And the answer there is 1.95. That means these can be scheduled with RMS. Now, by the way, this is independent from the utilization. If the utilization is more than 100%, you definitely can't schedule it, for sure. If it meets this bound, you definitely can schedule it. And if it's in between the bound and the utilization of 100%, then it's unclear, right? Here's another example, this one, and you look at this and you can't tell from looking at this that it can't be scheduled. It's 4 out of 10, 3 out of 12, 5 out of 15. Looks fine to me. Like if you presented those tasks to me, I'd be like, yeah, should be good, but it's not. The RMS bound for that is 2.33. So that one is maybe, but maybe not. Maybe not good, right? You guys with me? So just, there's the RMS bound, you get a number that's, kind of a big number that you're targeting 2 here, right? And then utilization is a separate way to calculate. You can calculate the utilization, and then in which case you're looking at 0 to 100%, right? Okay, so now there is a caveat here. RMS can achieve 100% utilization if the periods are mutually harmonic, if they're factors of one another. Like, if the periods are 20, 40, 80, then you can achieve 100% utilization. Okay, make sense? Okay, so then you might be wondering, well, what about like multi-core? Because back in the day, I mean, up until just recently, I think, right? Most microcontrollers had one core. But then suddenly, we ended up with multi-core controllers. The ones that we use in this class are multi-core, right? Although we're only using one, right? So there's been a lot of work in multi-core real-time scheduling. This is even harder yet, and this is an open problem in computer science. No one has a solution to this. There's a few approaches, but none of them are great. They all are limited to fairly small utilizations of the cores. So one approach is, well, one obvious approach, if you sit and think about it, it's kind of obvious, partition scheduling. This is where you just say, I'm going to take my cores and I'm going to assign half my task to one core and half the task to the other core, and then I'll just treat it like a single core problem, right? Problem solved, right? Then I just use the single core RMS algorithm on it, right? The problem is that there's a lot of different ways that you can make that assignment, right? Another way is global scheduling, which is where it's more like, global scheduling is more like how multi-cores work in a general purpose sense, like in Linux, where you assign tasks based on whatever core is available. Like any task could run on any core, right? That's how a regular, that's usually what you think of when you say multi-core processor. Any task should be able to run on any core. But that's global scheduling. The global scheduling is the hard one. So I found two algorithms for this. One's called rate monotonic first fit periodic scheduling. And the idea for this is that you assign a task to the first processor that passes the single CPU RMS schedulability test with the other tasks on it. So in other words, this is a greedy algorithm where you assign each task one at a time to a processor, right? Based on if when you add that task along with the other tasks you put on there, it meets the RMS bound, right? This guy has its own schedulability test. But this one's different. This one is where it's based on just the utilization. So you calculate the utilization, which is just add up all the execution times over the periods. And you have to check to see if that's less than m, which is the number of processors, times the square root of 2 minus 1. I don't know why I wrote it as 2 to the 1/2 power. That's square root of 2 minus 1, which is 0.41, right? Because the square root of 2 is like 1.41 something, right? So if you have, say, 4 processors, this is limiting the utilization to 4 times 0.41, right? Which means collectively, it's less than half of your capacity, right? Of your total system capacity. That's terrible. But that's the best schedulability test for this algorithm, right? Now again, you can still try to schedule beyond that bound, but no guarantee it'll work, right? And so this is an example of a, and this is partition scheduling, technically, right? So in this case, we have these tasks, and then the utilization here is 1.9949, which is okay because there's you would think it's okay because there's 2 processors. So you should be able to use it. You should be able to use up to 2, utilization of 2. But yet, but that's, I'm sorry, that's for 1 CPU rather, sorry. For 2 CPUs, the utilization would be 76.5, which is okay because that's less than 82%, which would be 2 times 0.41, right? Makes sense? Okay, so then we have, here's another example, and then, okay, so then there's global scheduling. So there is a EDF for multiple CPUs. And so, for example, as I mentioned, you have to think of this like every time a period starts, you have to calculate which tasks are ready at that point, right? Likewise, every time a task ends its execution for its period, you have to recalculate what tasks are ready, right? And then the tasks that are ready have to have their priorities calculated. So in this case, we start out with 1 to 5. Task 1 to 5 are ready at the beginning. So task 3 has the earliest deadline because it's coming up at 10, right? Which is indicated by this red line. So you can see the first vertical line is red, meaning task 3. So we're going to schedule task 3, but that's just on the first CPU. We're assuming 2 CPUs. So now we have another slot, another CPU. So what's the next highest priority task would be green, right? Green's the next line. So what's green? Green is 5, right? So we're going to put 5 on CPU 2, and we're going to run those two guys in parallel, right? Now, you know, T5 has a shorter execution time than T3, but that doesn't matter. What mattered was where these deadlines are, right? And then, so now we have to reevaluate after T5 ends, at which point T3 is running, and T1, T2, T4 are ready. So among those, the next one is probably this blue, 2. Yeah, so we're going to do 2, and we're going to put 2 over here on CPU 2, right? Now the challenge is yeah, we're going to leave it to run to completion here. No, are we? Maybe not, actually, because T2 could have been preempted whenever this red line crossed it, right? Because when this red line crossed it, that meant that T3 was ready to go again, right? And if T3 has a higher priority, then it could preempt T2, except it doesn't because we still have another CPU, right? Yeah. So anyway, let's see what happens. So then at that point, after T3 finishes, we have T1 and T4. Of those, it looks like T4 is 40. They're both 40, so we'll just pick one, I guess, right? So we'll go T1. Okay, so now T1 runs, but it doesn't run to completion. It's going to get preempted whenever T3 is ready to go again here, right? Now the question is, like I said, I mean, we could have preempted T2 and put T3 here, right? I don't know why I put it on I don't know why I chose CPU1, but we're going to use CPU1. Maybe because T1 has a lower priority than T2. So if we're going to preempt one of these, we should preempt T1, right? So we'll preempt T1, and we'll put T3 back on there, run him to completion. After T3 finishes, after T2 finishes, now we just have T1 and T4 ready. So we're going to run, I guess, it doesn't matter, they're both equal. So what are we going to do? We'll put T1. So now T1 has migrated CPU. So T1 got preempted on CPU 1, but it picks up back on CPU 2, right? At which point, T4 is ready at this point when T3 finishes, so we can run T4, but not for long because, yeah, like that T5 is ready there, right? So T4 gets a very short taste of the CPU, at which point it's going to get preempted by T5. And then T4 can pick up back again, but it gets another just short taste because it's going to get preempted again by T2, right? Okay, so that's the idea with EDF on multi-CPU. Oh, I just cut it off. I got tired of building the slide.
Well, I was just thinking because both of the deadlines were at the same point. I just thought T3 would have been preempted before T2 because it has a shorter period.
You thought which one? I'm sorry. Say that again.
Yeah, T3 should have run instead of T4.
Because see right here on T4 or after T4, both of your deadlines for you got a deadline for T2 and a deadline for T3.
Mm-hmm.
And I thought T3 would be preemptively ran instead of T2 because of
Oh, you're right. Yeah, that's a good point because T3 starts again there. You're right. Yeah, that's a good point. Yeah, nice. Nice catch. Yeah, that's he's right. The red line indicating the beginning of T3's period is obscured here. It's kind of hard to see, but yeah, technically T3 should be there. That's a good point. Cool. All right, I'll have to fix that. All right, so global scheduling with EDF has the wackiest schedulability test. So there's two conditions. So obviously the utilization has to be less than M times than M, the number of CPUs, right? That's common sense. But then there's this second condition. This is the one that's really strange. I don't understand how this was derived, but you have to calculate the greatest common divisor of the periods. Okay, and then you multiply the greatest common divisor by the ratio of each one's execution time to its period. And if all those numbers are integers, then you can schedule. Right? So for example, if you have that task set over there, and there's two processors, the periods are 40, 20, 10, 40, and 15. So the greatest common divisor is 5. 5 is the greatest divisor of those numbers. It's not 10 because we've got the 15 in there. And then you multiply 5 times the ratio of execution time to period to each one. So this would be 5 times 24 over 40 is 3. 5 times 8 over 20 is 2, and so on. And all those numbers are integers, so we're good, right? It'll schedule. And of course the utilization. Utilization here, by the way, is actually exactly 2, right? So this is utilizing every bit of 2 processors, and yet it can still schedule, right? Because it's EDF. But if you have, I think I changed one of these guys, I changed the period of one of them. So now the greatest common divisor is 4, because the periods are 40, 20, 12, 40, and 16. And so you do the same test and you get some fractional numbers in there. And so that says it's not schedulable, right? Okay, makes sense? All right, so that's real-time scheduling. So this now brings us to the next lab. This is our final lab. So we're going to try to get one of the motors working. Like the original goal was to get 3. So if you look on the boards, there's connectors for 3 motors. We're just going to use 1 for this semester, and we want to be able to control the motor. When I say control it, we want to be able to tell it how fast it should spin. All right. Now you might say, what's so hard about that? Yeah. Well, because the input to the motor is a PWM, and the PWM signal is actually, if I'm not mistaken, with a brushless motor, what you're controlling there is the torque of the motor, not the speed directly. Meaning that the speed, the rotational speed, depends on how much load is on the motor, as well as how much torque the motor is putting out, right?
You gotta do a little bit of that.
So the load on the motor is what's known as a disturbance in control systems, because you can't predict what the load is, right? And there's no clear relationship between the PWM duty cycle and the speed of the motor, right? Guys, so we want to create a closed loop controller where we measure the speed of the motor, and then in response to that, we set the PWM duty cycle, and the goal is to try to get it to rotate at a given set point.
Yeah.
Make sense? We can use a PID controller. So how do you measure the speed of a motor?
Well,
Anyone know?
it depends if the motor has that already in it.
It's got to be considered.
Yeah.
Motor.
Well, in a brushless motor, there's actually 2 ways. Brushless motors are comprised of coils, 3 coils, that energize in sequence that cause the motor to spin, right? So this is, I think, EVs, drones, they all use, every motor, electric bikes, pretty much every powerful motor is a brushless motor. But as it turns out, those coils are used to move the motor, but they can also be used to sense the direction, the speed of the motor, right? Because you get eddy currents in those as you turn it, right? However, my understanding is, I'm not an expert, my understanding is that that's usually not done because it's not very accurate to do it that way. Another way to do it is to use what's called a Hall effect encoder, right? Or there's other ways to do it where you can use optical encoders. But basically the idea is that as the motor turns, it puts pulses out, right? And the pulses are generated by fixed positions around the radius, right? So every motor with one of these rotary encoders will put out a certain number of pulses per rotation, right? Now in the last time I taught this course, we were using, you guys probably seen them around. We had this small motors, small DC motors.
Yeah, they're the little 3D printed things.
Missing the motor.
Yeah, we had some small ones. Those were from Adafruit. And they had 11 pulses, I think, per rotation, except they're also geared motors, meaning that the encoder was measuring the internal shaft of the motor, but that internal shaft would have to spin 50 times to spin the external shaft once because there was a 50-to-1 gear ratio, right? The motors we're using this semester have no gears, as far as I know, right? So basically the encoder is an accurate reflection of the external shaft speed. And they have 100 pulses per rotation, right, somehow, because these are way more expensive and way more powerful motors. And I have to caution you about that. They are powerful to the point of being dangerous.
Go put them on the table and turn them on.
Yeah, you don't want to spin these up at their maximum speed. They can injure you. So you want to be careful. These are, we don't know what they were intended for. We got them, basically off the black market in China. So we don't know if they were like, they're basically weapons grade motors.
Chinese weapon.
Yeah.
Yeah.
So that's the issue. Now the other thing is that the encoders, there's actually 2 encoder signals that come out. And the reason there's 2, they're basically identical signals, but they're out of phase from one another. And the phase is what determines the direction. So this is called quadrature modulation, the way that these work. However, in this lab, that's not useful to us because we're only going one direction. Right, so you only have to use one of the encoders. However, I read online recently that even if you don't use the directional, even if you don't interpret the phases of the pulses as the direction, you can still take advantage of it. Because if you XOR both the encoder signals, it multiplies the frequency by 4. So you get 4 times the resolution. So instead of 100 pulses per rotation, you get 400 if you XOR the 2 signals. You can effectively quadruple the resolution by XORing the 2 encoders. But we don't need to do that either. Don't worry about that. But I just keep that in mind. There is that ability. In fact, I don't think we can do that, actually, because I don't know if our hardware supports that anyway.
That's what I did. That's what I did when I first did this. I did 400 pulses per revolution by doing exactly that.
But how did the P count XOR?
I did it in software.
Oh, okay, okay. Okay,
yeah,
so
I used 2 channels of the P count and then added them. It's been a while since I did
but then what's counting?
2 different channels of the P count counted pulses off.
Oh, and then you just add the counts.
Yeah, and then I just added them.
Oh, okay. All right, that's another way to do it. Okay.
P count counted rising and falling edges, so 200 per thing. And
Yeah.
Okay, so all you have to do for this lab is you can just use the 100, but we want to use yet another peripheral for this, right? So it turns out on this chip there's a peripheral designed to do exactly this. But it counts pulses. It's called the P count peripheral, right? Now originally we were planning to have you guys program the P count peripheral like you program the RMT peripheral, which at the low level. But I think the impression I get from you guys is that that was a pretty miserable experience, right? So I think it might be better this time to just use the driver, right? Which simplifies the process greatly, right? Then you don't have to worry about, because I helped a lot of groups in here and I noticed that a lot of, maybe not a lot, but some of you spent a lot of time debugging, individual bits, errors, and, or clearing a field to 5 bits and, you forgot to clear it and you just added the bits in there and it caused issues. So I wanted to try to avoid that. I think having done it with the RMT is probably a good enough experience for you guys. It's kind of pointless to have to struggle with that again. And I found out that, and I think I mentioned this in my lecture when I talked about the RMT, I thought there was no driver for the RMT, but that was wrong. I suspected I was wrong when I said that. There is, Expressive has a complete driver library for every peripheral for NC. Everything is there.
The Arduino framework too?
Yeah, works. So it's true that the Arduino Foundation did not develop a driver, but they wouldn't have to because it's already available in Expressive, right?
Oh,
So-
okay. So you're including like the Expressive, like the ESP IDF driver in the.
Right.
Okay. I got it.
Right.
Yeah.
Yep. Yeah. So you can just use that. So let's see, lab sheet. I just got this done. We may end up having to update this, but this just talks about quadrature encoding, and then so the P count. So to use the P count peripheral, it's a little bit. The P count peripheral is very flexible, so it's a little bit obnoxious to set up, but still much better than doing low-level programming. So basically, all you have to do is include driver/pulse_count.h, and then there are 4 data structures, or 4 structures, 4 variables that you have to declare. The first 2 are handles. So the P count peripheral, I think there's 8 of them, and each one supports multiple channels, right? So there's this notion of a unit and a channel. A unit is just the P count unit, and each unit supports potentially multiple channels. And each channel is just simply a pin that you're measuring the counts on, right? So we just need 1 unit and 1 channel, but you still have to create a handle for both, right? You create a handle for that. So I called it my P count, and I called it my channel. That's just the naming convention I use. Then you have to initialize the configuration. And so there's a configuration for both the channel and the unit. So the unit config has this high limit and low limit for counts, right? The idea is this is clipping the count, a high limit and low limit. Now you might say, wait, if you're counting, how would you ever hit a low limit? That makes no sense. Because you can set it up to decrement the counter under certain conditions. So for example, you can set it up to decrement the counter on like a falling edge, or there's a secondary input called the level. There's a pulse and a level, like an auxiliary signal called level, like you can use as a flag to figure out if you're decrementing. But we're not decrementing, so forget all that. We're just incrementing. So you can set the low limit to -1. And the high limit, now here's the deal with the P count. The whole purpose of the P count is to not bit bang, is to not have the software counting. Because this is not the job for the CPU, right? This is the job for the peripheral. You don't want the CPU using time counting pulses. So the idea is to achieve concurrency, right? You want the P count to do the work of counting the pulses, and we want to be able to check that count as infrequently as possible, right? Which means that the high limit has to be as high as possible, because if you reach that high limit before the software checks and resets the count, you're done, because it'll saturate at that high limit, right? It'll stop counting. Now, through trial and error, I found that the highest possible limit for that is 2 to the 14th power, 16,384. If you set it any higher, you get a runtime error. And then there's this interrupt priority and flags. You can just set those to 0. And then for the channel config, this one has pin numbers in it. So this is the edge pin number and the level pin number. Again, like I said, you can have 2 pins assigned to this per channel. One of them is just a level and one of them is an edge. We don't care about level, so we're just going to set that to -1. And for the edge, we want to set that to whatever pin you want to monitor. There are 6 of these pins, though, because there's 3 motor connectors and an A and B quadrature signal for each one. You can choose whatever the 6 you want to choose, and I have all the pin numbers in the document. Okay? Okay, and then invert and all this other stuff you just set to 0. Okay? Okay, then once you set that up, you have to create a new unit, you have to create a new channel, you have to set the edge action, which in this case we want to increment on rising and decrement on falling. Alex just said he incremented on rising and falling, which I don't care if you do that. You just have to keep in mind that that will change the count to 200 per revolution. And then you have to clear the count, enable it, and start it. Okay? And then whenever you want to check the count, it's very simple. You just say p count unit get count and p count unit clear. You have to clear it, right? So the problem here is that we're measuring, what are we measuring with count? We're measuring how far, basically how many revolutions, how many times it's spun, right? But we don't care about that. We care about velocity. We care about rotational speed, right? So you're going to have to calculate the derivative of this to get the speed, right? So you'll have to measure the count twice and look at the difference, right? So keep that in mind. Okay, now, what about the real-time systems? Where does that come into play? Okay, well, as it turns out, these chips are running a real-time operating system called FreeRTOS. And the problem is that, now let me, so real-time operating systems in general are extremely expensive. There's one called, the most famous one is called, I can't remember, I always forget the name of it. There's a really famous one, but it's like $40,000 a seat. It's outrageously expensive. There were efforts over the years to make Linux have a real-time variant. You know, companies came up, I think Wind River was one of them, but none of them, as far as I know, really succeeded. But this one is called FreeRTOS. It's free, but here's the catch. The catch is what makes a real-time operating system really a real-time operating system is the schedulability check that I just got done lecturing about. That thing I talked about where it determines whether a schedule is feasible, that's what makes it $40,000 a seat. FreeRTOS does not do a schedulability test. It'll let you schedule things that can't be scheduled because it's dumb like that, right? But at least it allows you to create real-time tasks that are schedulable, that are scheduled and preemptible, right? As compared to what? As compared to you guys writing in your loop function all the code necessary to figure out whether it's time to read the P counter or run the control law or update the PWM, right? That is kind of error prone, right? You guys you got a little taste of that in Lab 3 when you had to manage the LEDs and the audio. That sucks, right? It would be better if we could just tell the operating system, look, do this every so often, do that every so often, right? And that's what we want to do. We want to manage the count every so often. We want to manage the control law every so often, right? And that's what FreeRTOS will do for you. So all you have to do to use that is you just have to say include FreeRTOS, FreeRTOS.h, include FreeRTOS task.h, right? Then it's really simple to set up. You can create a task handle, and you can create a task, and this would be in your setup function, right? And so creating a task is you just pass it a function pointer. You just define a function, and you pass it the pointer, and it will create that task and it'll schedule it, right? The part that's a little weirder, though, is once you have the task, how do you make the task periodic? Because in FreeRTOS, once you create a task, if you exit that task, if you exit the function that you called in that task, it's gone. It'll destroy the task, right? So you want to put that task, you want to put an infinite loop. But if you have an infinite loop, what makes it periodic? What makes it appear every 10 milliseconds, right? And then run till completion? Well, for that, use a special function called vTaskDelayUntil, right? So you can set this up exactly the way it's set up here, is that you have to keep track of the last wake time and the time increment. The last wake time, you don't worry about that. That gets set by FreeRTOS, using the task get tick count. But this, no, I'm sorry, actually, sorry, scratch that. That actually gets initialized with task get tick count, but it gets updated with the delay until. So the delay until function is going to update this variable for you, right? Because it's passed by reference here, right? So you don't have to worry about that one. The only one you have to worry about is the time increment, and that's going to be your period, right? And so to do that, you can call this helper function called milliseconds to ticks, right? Now, what's a tick? A tick, FreeRTOS has a notion of a tick. I don't know what it is. It's just a unit of time that it's some unit of time, right? But you can convert time to ticks, or at least milliseconds to ticks, using that function, right? So if you use this template, you can create a periodic task, and it's actually a true periodic task. It's not dependent on when the task is, like for example, if you guys were doing this manually, you would run the task and then calculate the next time the task should run, right? But when you calculate that, you're calculating it relative to when that task started. What happens if the task was delayed, right? Then there's no way to account for that, and you end up getting jitter in the period, right? This will guarantee a 0 jitter period, right? So even if for whatever reason this guy gets delayed, it'll still it'll fire, the next time it fires will be exactly whatever the period is from the last time that task became ready. It makes sense when its period started, right? And then you could just insert your code here, and then you got it. Now I mentioned though, here's the issue with this is that FreeRTOS doesn't have a schedulability test. So how do you even know if your tasks are requiring more than 100% utilization of the CPU? Now you might say, well, there's 2 CPUs, right? No problemo. No, it only works on, I don't know why there's 2 CPUs, only one's used. There's only one. Well, it's effectively 1 CPU. But so you can't exceed 100% utilization. So how do you know what your utilization is? Well, FreeRTOS has hooks. You can have it call a function whenever a task becomes ready or a task ends, right? Unfortunately, Arduino prevents you from using those, because the only way to use those is to use the native expressive operating system and compile it with the hooks. You might say, compile an operating system? Why would you do that? Well, okay, real-time operating systems are not like Linux. You actually compile them every time you change your code. Because real-time operating systems aren't like Linux where you log in and you get a prompt. A real-time operating system is actually really just a runtime library. There's no interactivity. You compile it. So FreeRTOS is compiled every time you change your code. You compile the entire operating system. And when you do that, you can put hooks in that are called, hooks meaning functions that, callback functions that you provide that it calls when certain things happen. But Arduino's like, no, not happening. Won't let you do that. I tried. So, but there's an easy workaround. The workaround is you can have them calculate their own utilization, because at the beginning of this for loop, you can actually measure what time it is, right? And then you can accumulate the total time the task took right before you call this v task delay until. Right? This v task delay until puts the task to sleep until its next period. So if you measure the time before, right as you start and right before you put yourself to sleep, and then you accumulate that into this global variable, task A total, you can keep track of the running amount of time spent in that task, right? Meanwhile, at the beginning of your setup loop, you can record the time, you can record the time that the whole system came up. You know, because when the setup is called first, right as your Arduino code comes up. So you can measure the startup time. And so as a result, you can calculate the utilization of each task independently by simply looking at the total time in the task divided by the total overall time since you brought the system up, right? That's pretty cool, right? Now notice I'm using this ESP timer get time instead of micros. Both are the same. They both return microseconds on the clock, right? But strongly recommended by a nice man on the internet that this is more accurate than micros, but you can use either one. But this is just the micros, the ESP32 specific micros function. It's supposed to be better than the Arduino micros. Make sense? Okay, so the idea is that you would just have 2 tasks, and then the loop task is still going to run, but it's going to run at the lowest priority. And I kind of brushed past this, but when you create the task, one of the options for the task is the priority. So if you want to do RMS scheduling, you would simply set the priority when you create these tasks to whatever the period is, right? And then you have an RMS scheduler. However, in this case, I recommend that you just set these all to the maximum because you'll probably have the same period for both, right? And so there's a thing called config max priorities -1 that will give it the highest priority. And for whatever reason, in free RTOS, higher priorities mean more priorities, right? Unlike RMS, which is lower period means higher priorities, right? Okay, so, and then finally, for controlling the motor, we can just use a PID controller. You guys have all done this in robotics. So the error is the set point minus the motor speed, and then you can calculate the derivative and the integral of the error, right? What's the motor speed? The motor speed should be in RPMs. And you can just set that in your code as a constant. You don't have to make it like something you could type in at runtime in the console. You're welcome to do that if you want, but I'm fine if you just set the RPMs as a constant, right? In the last version of this class, our goal was 1 RPM because we were trying to create a second hand for a clock that spins at 1 revolution per minute. I think Alex said these motors don't go that slow, right? Because these are not geared.
The lowest you can go here is about 60 RPM, so that's 1 rotation per second.
Yeah.
If you go any slower than that, you're going to start having problems.
Yeah.
Yeah, I'd aim for that or maybe 120 RPM. And you can power these motors on anything from 12 to 24 volts. So
What's our upper limit?
what?
How fast can we go?
Yeah, what's the
Oh,
upper
you-
limit that we're supposed to avoid?
Oh,
Thousands of RPM.
yeah.
I
Don't
Don't put anything on the shaft though, because that thing will vibrate like
Yeah.
crazy.
be conservative with it. These motors are, so the old motors, we deliberately bought them geared with a 50-to-1 gear ratio because we wanted to be able to control them at very slow speeds, right? Because these don't have gears on them, they're not designed to go slow.
you can always just say just assemble a few drills, old drills, and slap a gearbox on it.
Yeah, that would be, if we had something like that, that'd be nice. Okay, so any questions about that?
You can grab them to the end of it.
Okay, so I've got so we've extended lab. If you need more time for lab 4, you can have it till the end of this week. And technically, it's due on Friday, but remember there's no late penalty assessed on the weekend, so you have till technically Sunday. But the sooner you get done with that, the sooner you can start this lab. This lab I have due on reading day, which is the Tuesday after finals week. And so, anytime you can finish it before finals week works. We will have a final. It'll be open all during finals week. It's like the midterm, and it'll cover the control. It'll be comprehensive, but it'll include the control theory and the real-time systems on it. Also, I have a quiz on the real-time scheduling. That's up on Dropbox. So on Blackboard. That's due on Friday, and I haven't put these slides up yet. The lecture slides. I'll put the lecture slides up today. But the lab sheet is on there, and the submission box for the lab is on there. Okay? All right, thank you.